next Thursday. So I was wondering how to make up the class, and we were discussing possibilities. And the one we came up with was next Tuesday we'll double up this class. Is that going to be an inconvenience for you? I'll be recording everything on Screencast-O-Matic, so you'll be able to catch anything you can't do. Do you have a time restriction?
I don't know. I might have to wait. I'm not sure yet.
Okay. So what we'll do is double this class on Tuesday, and then we'll have linear algebra right after that class is over. And then I'll be gone the next Thursday, and then the next Tuesday we'll have this class regular, and we'll double our linear algebra. That's how we'll make up the time for that. And I think that Cameron's getting ready to pick it up and throw it against the wall, but I'm not sure. Okay.
That's good. For now. Yeah. Probably need to get on with it anyway.
Okay. So we are recording now. I just wanted to get that on there so that other folks will know that too. So let me just reiterate or say now that we are recording. Next Thursday, I will be out of town or leaving town, probably already out by this time of the day. So we will not have class next Thursday. So what we're going to do is on Tuesday, we'll start at 9:30 and go straight till 12 o'clock, okay? And then for those who may be in the linear algebra class, we'll pick up linear algebra. We may 12:15 or something like that and go to 1:30, okay? And then Thursday, I'll be out of town. The following Tuesday, we'll have differential equations, regular time 9:30 to 10:45, and start linear algebra at its regular time 11 o'clock, and it will run until 1:30. So that way we'll make up both of those classes. Now, I forgot to say anything to my 8 o'clock class this morning, but we'll work that out on Tuesday. And I'll figure it may be for that one, since it's such a big class, I'll not be able to do anything more than just record it when the most people can show up. So, anyway, that's how we'll go for next week. Yeah, I know I'm going to be in the edge of the screen, but I'll get up and move as much as I can. I just can't move much because of cord limitations here. Now, my mark here in the book is that we were on example 3, but we hadn't progressed too far in example 3. So let's go. Any questions before we proceed with this? All right. We'll try to. It's on 2.4, page 67. Example 3 is where I have it marked. Okay. All right. And I'll go and write it down again. Oops, let me get my pen redone. Okay. dy dx is equal to x y squared minus cosine x sine x divided by y times 1 minus x squared. Okay? With the initial condition y of 0 is equal to 2. Okay. Now, what we did before was rewrite this, and by the way, let's just confirm what we think we already know here. We can't if we multiply both sides of that equation by y, then you get the y and the dy together. But then you would have the the stuff over here, one of these would have x's and y's, and one would have only x's. The only x's you could put on the other side, bring the x and y one in here, but it wouldn't be a linear equation because of the quadratic. So the linear part we wouldn't get, but and that was the model, you know, for. So I don't think there's anything we can do. We certainly can't separate variables. Comes close, but no cigar. Not really as close as you might think. So what we're going to do is write it in our sort of standard form for these exact equations, okay? Multiply both sides of the equation by your denominator here, and that gets that with the dy, and then write it in differential form and get the dx on the other side. So that gave us y times 1 minus x squared. I'll put it like that, dy. And we want this all on the same side. So I'm going to do plus, I'm going to move this over, cosine x sine x minus xy squared dx is equal to 0. Now that's our standard form. And I'll probably forget, but you probably should write y of 0 equal 2 just so you don't lose it. Yeah. But that's the your m n, right? So m of xy and n of xy. Okay? And last time we did the partials and we verified they were the same, so we won't go back and do that part. Okay? And they came out being minus 2 xy. Oh, wait. No, I didn't do that right. This is our m, this is our n, because I put the dx. Our standard form is the dx first and the dy second. And we usually name them otherwise. So I really should have turned those around. I just realized I did them backwards. I hate that. Okay, let's get them right this time. Okay, the dx, we're going to do the cosine x sine x minus xy squared. That dx, whoops, okay, I forgot that. And over here it's y times 1 minus x squared dy. Okay. It's not efficient use of space, but we got it. Okay. Now the m and n are right. We got them in the order. And we've already verified that the partials match, so we can do this. So what was the next step then? We assume there is a solution function, f of xy, oops. Okay. Yuck. All right. Okay. F of xy equals c. There's some function that will satisfy this. Okay. So what we do then is take the partial of this f with respect to x. Okay. And when you do that, and what we want that to be is this thing right here, because you want the partial of f with respect to x dx, the partial, that's what. So you want this to be that, the m. okay? Equal cosine x sine x minus xy squared. Okay? So basically, we're going to integrate this, right? Or write this in differential form. Change them to d's, you know, pretend the y's are just constants and you're not really doing it, okay? So then you have f is equal to, okay? And if you integrate this, let's do the first one first. Why not, okay? Do we need to split that? Let's do it. Integral of cosine x sine x dx minus the integral of x y squared dx. Okay? What you got there? Yuck. Okay.
No, it's backwards.
No.
The anti-group.
Substitution ring a bell? Let's let u equal sine x. Then du equal cosine x dx. And all you got here is then the integral of u du. Okay? And over here, remember you're integrating with respect to x, so the y is a constant, so that y squared is out front, and the integral of that would be,
Or no, 2. No, it's 1.
huh? No, you're not differentiating, you're integrating.
It'd be
X squared over 2. Okay? And if you do that first integration there, that would be u squared over 2 minus x squared y squared over 2. And then you could do a plus c, but let's go on and plug in what the u is, or u are, or however you say that. That's sine x. So this is sine squared x over 2. Well, how about this? Let's just take the 1/2 out front. I might regret it later, but it just seems a little more reasonable to do it this way. One half of sine squared x minus x squared y squared. Okay. Now, probably need a plus c in there. And that's then the sort of the question is, where am I doing the, I'm sorry, you could do it either way. The book is doing df dx. No, I got it. I mean, they just did it a different way. Sorry about that. I'm trying to figure out why they did it this way. And I mean, it's exactly equivalent. We got what they're calling the h of x. We got to 1/2 sine squared. They did their substitution the other way and got negative 1/2 cosine squared, which it really doesn't matter. But what I'm trying to see is why they have they started the other way. They did the df dy. I jumped down and was doing partial of f with respect to x. And I don't think it really matters. Let's try it. Let's continue the way we're doing now. The other part here that I don't have is plus what they're calling h of x. The point is my h of x is not the same as theirs, so we could call it something else if you want to. Do you want to, or are you happy with h of x? Okay. Not h of x, h of y. Maybe we should call it something else. Can I call it g of y? Because I'm afraid you'll think these are yuck. I'm going to call it g of y. I don't think they're going to use g anywhere else in the problem. Okay. Now, that's our f. Okay? Now, we want to take the partial of that with respect to y. And again, I did it. I just looked up and didn't see. My eyes captured on the wrong line, but it doesn't matter which way you do it. I don't think one way may be easier than the other, but let's see. So let's do the partial of this f that we've come up with here, partial of this f now with respect to y, and that would say again. Yeah. No, we're going to take the partial of this one, and then we're going to match it up with the n. Yeah, at the end, but we're not going to do it yet. We're going to actually take this one. I don't remember to get that out of here. I just don't. Sorry about having to do that in class. Okay, so let's take the partial of f with respect to y. This f that we've got here, this function right here.
Oh, okay.
Yeah. So that's going to be with respect to y. Well, notice that first term has no y in it. Okay, so that disappears, the 1/2 sine squared x. Don't have to do anything to that one. The next one does have a y in it, so that's going to be a minus, and 2 times 1/2 would be 1, so minus x squared y. Okay?
Would it not be negative 2x squared?
Okay. Well, the 1/2 is still here.
Oh, okay,
Yeah.
because you're still multiplying.
Yeah.
So it would be, but then you multiply by
Yeah,
one.
but I'll have to go absolutely right. Okay. And then you got a plus g prime squared. G prime of y. That is a real derivative, dy dx, because that has no x.
No y.
dg dy, it has no y dependence. Okay. I mean no x dependence at all. Okay. Now, what we want that to be, and by the way, if you rearrange our n up here, you'll see that this n is y minus yx squared, right?
So we need,
The yx squared is already taken care of. The g prime has got to be y. So this has to equal y. And we'll integrate that one, okay? And that gives us,
y squared over 2.
yeah. So g of y is equal to y squared over 2. Okay? Plus some constant c. All right. Now, what I think I'm going to do here is erase this stuff in the middle here. I don't think I need any of that. Okay, since I erased the M, I guess I'll erase the N too. I didn't mean to, but I did. Okay, so what is my F? Yeah, here it is. F of xy is equal to 1/2 sine squared x minus x squared y squared plus y squared over 2 plus c. Okay? Now, when y is equal to, when x is equal to 0, y should be 2. Okay? Okay. Yeah, that was the initial condition. Okay? Okay. So, yeah, I was trying to get it the same way they do. And what they do is they don't call it the F anymore, though that's really what it is. This thing is F. But they say this is equal to C. And that's why F is equal to C. So they put the C here and not back here. I'm just trying to balance and get it looking the same way they do. Okay? Now, again, the other thing they did was multiply everything by 2. Except, what has happened to their x squared y squared? I thought we had that right, but they don't have it. Oh, yeah, they do. It just shows up later. Okay, sorry about that. But it still seems like that should have a 2 in it, and it doesn't.
Where do you see the 2?
Say again? I'm trying to match mine with theirs, and since I approached it slightly differently.
Well, they got the negative 1/2 cosine squared x, which is your 1/2 sine squared x.
Right.
Then they have y squared over 2 being multiplied out through 1 and negative x squared. So that gives you your y squared halves and then your.
Yeah, but you see. Oh, I see what I did. I took off my parentheses, so I see. So that 1/2 is in there. Yeah, no, I didn't distribute the 1/2. I lost the parentheses, but didn't distribute the 1/2. So yeah, that does have a. This is also over 2, because that 1/2 was in front of that. So what we did is just lose the 2's and incorporate that into our C. So yeah, we're back basically at the same place they are. Okay? Now, so, wish I had more room on the board. This one actually you can solve for y, because like they did, you can factor out a y squared, and that gives you a 1 minus x squared. Okay? All right. So let me try to, this will just make it easier for our determination, I think, if we do it that way. Y squared times 1 minus x squared is equal to c minus sine squared x. All right. Right. Yeah, and let's go on and do that. 1 minus x squared. And now we'll plug in the 0.
Well, still got to take the square root.
Well, we can square,
After
yeah, we can square the 2 too, you know. But this would give us then that y squared is equal to c minus sine squared x over 1 minus x squared. Okay? Now, if you plug a 0 for x, that just gives you a c in the numerator and a 1 in the denominator. So y squared is equal to c. Okay? So y is either, yeah, maybe we do need that.
Y equals square root of c.
Oh, but yeah, but y is 4. So, I mean, y is 2.
2.
So that would be c is equal to 4. Okay, that's what I would say. Okay. And somehow they got it to be 3. That's where I'm having difficulty seeing that. Because when x is 0,
Y is 2.
y squared is c. And y would be 2, so that would be 2 squared. Now, is the fact they used cosine rather than sine, that's probably it. Let's try that. Okay.
Wasn't what we did legal?
Huh?
We
Okay.
substituted in the sign
Yeah.
and all that.
Yeah.
It's
Let me clear some space here.
still,
I think I'll clear this clear this bottom thing. I don't think I need that anymore. I hope I don't. I lost my integral sign. Okay. All right. There's the equation we got, that our equation, if I'm writing it right, is y squared is equal to 4 minus sine squared x over 1 minus x squared. Okay? Right.
wait a minute. Sine of 0 is 1, right?
Sine of 0 is 0. Cosine of 0 is 1. That's where I think the problem, the thing's going to come out right. Okay? Now, what if we wrote, instead of minus sine squared, we wrote,
Cosine plus 1.
I've got to do that, sine squared x plus cosine squared x is equal to 1. So
1 minus cosine squared x, which is still 0.
yeah, but, so sine squared x is 1 minus cosine squared x. So this would be 4 minus 1 plus cosine squared x over 1 minus x squared. And that's where they get the 3. 3 plus cosine squared x over 1 minus x squared. So yeah, since they chose cosine, they got the constant of 3. We chose sine, we got the constant of 4. It's the same thing, because Pythagorean identity there makes it the same. So we did get the same answer. Okay? Went about it differently, but we got the same answer. Okay? So they get y squared times 1 minus x squared minus cosine squared is equal to 3. Yeah. Same thing.
So, if this were something on a test or something, that would be kind of confusing.
Yeah. No, when I'm working a test question and I see an answer that's different, but looks like they're related, I work it out to see if they are the same. I do. That's what takes me so long to grade these kinds of tests, you know, because I make sure if I'm marking an answer wrong, it is indeed wrong. So I would have done that same thing if it would come up. Now, I got it out of order. We should have started with the partial of alpha with respect to y, but this just illustrates it doesn't really matter, okay? It may have been a little easier doing that one because you wouldn't have had the sine cosine stuff, and then maybe it would have naturally come out using cosine squared rather than sine squared. But that way came out really nicely using sine squared. It doesn't really matter as long as the answers would have plotted just the same. So let's move on. Integrating factors here. Recall from section 2.3, the last one we did, that the left-hand side of a linear equation, and let me write that down. All right, to delete this, erase this, okay. This is our reminder. Y prime plus P of x y is equal to f of x. Okay, that was our generic form for a linear differential equation. That's why I said this one you could have almost gotten there, except you would have had a y squared here, and that throws it out of being a linear. Okay, so you had the y prime, okay, your f of x, you could have separated that, okay, but you didn't have y, you had y squared. So we couldn't have worked that. But anyway, recall from this, that can be transformed into a derivative when we multiply the equation by the integrating factor. And you remember what that was, okay. The same basic ideas sometimes work for non-exact differential equations. M xy dx plus n xy dy is equal to 0. Okay, that's exactly what we did before. And this time the integrating factor is not going to be named the integral. You know, we're not doing that. We're just calling it an integrating factor mu of xy. Okay, the integrating factor is going to be mu of xy. Okay, now if we multiply both sides of the equations by that, sorry, you get mu of xy, m times m of xy dx plus mu of xy n of xy dy equals 0, because multiply mu by 0, you still get 0. If you can make that an exact differential, like we just did. Now, let's time out. The assumption here, this is not an exact differential, meaning what? Partial of this with respect to y is not equal to the partial of that with respect to x. But if you can multiply this by something and that by the same thing, and now make that so it is exact, that this thing, the partial of this thing, is equal to the partial of that, you know, partial of this with respect to y, partial of that with respect to x. If it is exact, then you can proceed with this. Not the original, but this one, okay? Because those are equivalent equations. That's the point here, okay? If you can make that exact, in an attempt to find the mu, we turn to criterion 4 for exactness. What? Okay, you might ask. What is our criterion 4 for exactness? Go back to, that was exactly what I said. The partial of that with respect to y equal to the partial of that with respect to x. I'm sorry, I thought they were doing something else. That's what I already said, okay? Equation 8 is exact if and only if, and here's how you, now this is, I didn't show you this terminology, but I'll do it now. Partial of mu xy m xy with respect to which one? Y equal partial of mu xy n xy. I need an extra parenthesis there with respect to x. Now, rather than having to write that all the time, here is the shorthand for partials. Okay, mu m sub y. That means partial with respect to y equal mu n with respect to x. Okay, that's our shorthand there. Okay. Second. Yes, it really does shorten it. Okay. Now, those subscripts denote partial derivatives. Now, by the product rule for differentiation in the last equation, okay, product rule, same holds here. Hope you can follow my notation here, but that says mu sub y m plus mu m sub y is equal to mu sub x n plus mu n sub x. Okay? Okay. Now, next step, get your mu's on one side and partials of mu's on the other side. Okay? So in other words, we're going to subtract the mu m sub y from both sides and add the mu sub x n.
Shouldn't that be subtracted?
Not subtract, I'm sorry. Don't know where the brain is today. Lack of sleep, I'm going to say. Okay. All right. Okay. Yeah, subtracting that from both sides. Now, where am I going to go? Let's go up top. Okay. These disappear here, those disappear there. So what we have here is, they leave those together. Except they have, I'm trying to keep the same form, the book. I did it backwards from what the book did. They subtracted the m's. No, they didn't. Yeah, okay. They reversed and went the other way. I'm sorry. They kept this on that side. Yeah. So I'm going to reverse all that up here. Negate everything. Mu m sub y minus mu n. I can't write my n's well. Okay. Mu n sub x is equal to, reverse these two, mu sub x n minus mu sub y m. Okay. And I switched sides and I didn't need to do that. Goodness gracious. Too many things here. Let me rewrite that. Mu sub x n minus mu sub y m is equal to mu times m sub y minus n sub x. That's how they leave it. Not that it matters, but I'm just trying to get it so it looks the same. Okay? I don't think I'll need this anymore. Okay. Now I've got it looking the same way they do in the book. Okay? Now let's pause for a moment here. The mu's we don't know. Okay? We know the m's and the n's, and we have already taken m sub y and n sub x, right? Okay. And we knew this is not 0, because if that were 0, we wouldn't have had to multiply by mu. That would have been exact to begin with. So, basically, we already had this and that. They're not the same, so subtract them. And what we're wanting to do then, and we already know m and n, because that was given originally too. And what we want to do then is find the mu so that that everything here fits. Okay? So it says although m, n, m sub y, and n sub x are known functions of x and y, the difficulty here is determining that unknown mu, okay, from this equation. And that we must solve a partial differential equation. Okay? Since we're not prepared to do that, we make satisfying assumptions. Okay? Suppose that mu is a function of one variable only, not x and y, just one. Say x. Okay? In that case, this is derivative of mu with respect to x, and this is 0. Right? Because there is no dependence on y. Okay? And this, of course, is a function of x only as well. Okay? So, that then leaves us, if we adjust with here, this going away. So then we have, yeah, they do write it this way. D mu dx, and that is a derivative, not partial, because it's only of respect to x, would be equal to mu times m sub y minus n sub x divided by n. Right. Okay? And that's what they got, except they put the mu at the end. Okay? On the other side. So I'll do that too. M sub y minus n sub x over n times mu. All right. Now, here's the problem, Houston. This only depends on x. That was our assumption. This only depends on x. That's right. But these depend on x and y. Okay? So how are we going to reconcile that? Okay? It just doesn't seem fair. Okay? However, if after all obvious algebraic simplifications are made, that quotient, my minus nx divided by n, turns out to depend solely on the variable x, you're great. If that can work, if that works, okay, then your assumption that mu depends only on x is validated, okay, and you can do it, okay. And then that is a first order differential equation now. I guess you can say that. Yeah, because it's only got dy dx, okay. All those other things are balanced out, okay. Okay. We can finally determine mu because then, now this is all contingent on that thing, your y's canceling out, and you only have a function of x, okay? We can finally determine mu because that equation right there is separable. Because the y's are going out here, this is only a function of x, that's a function of x. Right, that differential form, so your dx is there, and your, I'm sorry, this is mu. Divide by mu, okay, write it differential form with your x. That depends only on x, and that is derivative with respect to x. That's going to be a log mu, right? And with that being a log mu, you can then write that. So they don't say this. It seems like they should. Let me write what I just said. D mu over mu, that's dividing by mu, is equal to this m y minus nx over n. We are assuming all the y dependence disappeared from that, and that's only a function of x. And then you have dx over here. When you integrate this, you get natural log of mu is equal to this thing, which is some function of x, okay? And hopefully you can integrate that. Well, then you can say that mu has to be, take the e of both sides, e to the integral of this thing, m y minus nx over n dx. So it's no longer a p, it's that thing, but it's sort of taking the same place off, okay? So that is our integrating factor. Similar to before, it was e to the integral of px dx. Now it's mu is e to the integral of whatever that thing is, which hopefully is a function only of x. Okay. Now, if that didn't work, and there's a good chance it didn't, that this thing doesn't turn out being a function of x alone,
Would you try to
then try it with respect to y. And reverse that and see if nx minus my over m, is that a function of y alone? If the first one doesn't work, then try that, okay? And if that does work, then you have d mu dy is equal to n sub x minus m sub y over m, what we've got here, times mu. Okay, so you would have it the other way.
divide and integrate?
Right. So basically, again, think what you know and what you don't know. You've already determined this. You've determined that. So, and you know what m and n is. So see if the difference of those two divided by n gives you a function of x alone, or the difference of these two divided by m gives you a function of y alone. If either one of those work, you've got your integrating factor.
And if they don't work,
You can't do it this way. You know, do it numerically or whatever, you know. It just isn't possible. So, I know that I'm going to regret doing this, but I've just got stuff all over the page. So I'm going to erase all this. And here's the summary. Okay. Here's where we started. M of xy dx plus n of xy dy equals 0. There's your initial equation. Now, on the side you did partial of m with respect to y, and you did partial of n with respect to x. Call this fact. M sub y n sub x. Okay? You calculated those things. You saw if they were equal. Boo hiss, they're not. Okay? So, subtract one from the other. Okay? Well, let me not get ahead of it. Okay? That's what you have. You've calculated those. You found out they're not equal to each other. So then subtract n sub x from m sub y, and you do m sub y minus n sub x. Okay? And divide that one by your n. And see, is this a function of x alone? Just do it. See what you get. Then, if that's the case, then your integrating factor is, the mu is e to the integral of this thing, m sub y minus n sub x. You've already figured out what it is. You don't have to write it again. You've calculated. You just put that in here over n dx. It's all a function of x integrated. Okay? If not, okay, sort of a algorithm here. If the answer to that is no, not a function of x alone, then you investigate and see if n sub x minus m sub y divided by m is a function of y alone.
It's like a flip chart.
Yeah, I was trying to think of that word. Okay? If that's yes, then the integrating factor is e to the integral n sub x minus m sub y over m, which you already know all those pieces, dy. Okay?
You know how you wrote yes over the arrows?
Yeah.
You should probably change the type of top one to an x.
So what?
To an x, because the top one's an x and the bottom one's y. I was confused at first why you wrote a y there.
Oh,
Yeah, because that one's
meaning
like
yes or
a
no.
function of x, and then this one's a function of y.
okay.
First I thought you were labeling.
Yeah. And this is a no here. Okay.
I didn't know what I thought that was L.
Oh, no. Yeah. Yeah. If the answer to that is, if that is a function of x alone, you've got your integrating factor. If it's not, flip it around. Okay? Is that a function of y alone? If it is, you got your integrating factor. If not, not going to work. Okay? All right.
That is time.
It is time. Oh man, just when we're beginning to have fun here. Okay. But we're always having fun. Sorry about that. All the projector stuff and everything else. Homework exercises here. Do any of the odds 1 through 19. Do any of the odds 21 to 25. Do 27. Do 29. And do 31. Well, wait. The 29 and 31, because we haven't actually done the examples with it. You can try them if you want to, but you can stop there. Once we do example 4, you'll be able to do them all. Okay? Now, sorry we didn't get more done today. 2.5 we'll do substitution. And 2.6 we'll do, it's real short, we'll do some numerical methods, which is what happens if both of these turn out no. Okay, so we'll go on from there. Hopefully next week we'll finish this chapter and I'll give you a test. All right, we'll see you. Have a good weekend.